Oftentimes when we're working with probability, we are looking at multiple events occurring. These events could be things that affect each other, or they could be events that don't affect each other, but they all add up to the probability of all these different events occurring, and they're called compound events. So an example is what's the probability of, that should be flipping a coin, so flipping a coin and getting tails 3 times in a row. We have 3 different events that we're looking for: getting tails, and then getting tails again, and then getting tails yet again. So those are 3 different events. And so we can illustrate this one with a tree diagram. If we flip a coin, we can get heads or we can get tails. And then once we get heads here, we can flip again and get heads or tails. And the same, if we flip the coin again here, we can get heads or tails. And then if we flip the coin the 3rd time, we can have heads or tails here, heads or tails here, heads or tails here, and heads or tails here. So there's flipping a coin 3 times: heads or tails, and heads or tails. These are all the possible outcomes. You follow any branch to find an outcome. So there's a total of 1, 2, 3, 4, 5, 6, 7, 8 different possible outcomes. So our total outcomes are 8. We want to find the probability of flipping that coin where it's tails, tails, tails. Well, there's only one branch here. This branch right here, where it's tails, tails, tails 3 times in a row. So there's one event. So the probability of flipping tails 3 times, the number of events is 1. But it's what's the probability in each case? And so the probability is taken into a factor each case. So we have 3 events. So normally it's 1/2. But here, there's one case of us flipping tails. And then there are 8 total possibilities. So the probability of flipping tails 3 times in a row is 1/8. Now, just a connection to doing, say, a true-false test. What's the probability of guessing 3 true-false questions right? 1 in 8. Just for comparison. So we have, again, our possible outcomes, and then our total number of outcomes on the bottom there, and then our wanted outcomes, which is all tails on the top, 1/8, and then 1/8 is going to give us 0.125 as our decimal. So these are compound events that do not have any effect on each other, so they're called independent events. So in this case here, I flipped the coin and it was tails. Because the first flip was tails, it could still be heads or tails. It won't affect the next option. The next time you flip, it could still be heads or tails. There's an equal chance. So there's a 50-50 chance each time. So there's no effects. These are called independent events. They're each independent of each other. And another example could be the probability of your favorite hockey team winning their next game and the probability of your favorite soccer team losing their next game. If your favorite hockey team wins, it has no effect on the soccer team losing, and vice versa. These events have no effect on each other. They're completely distinct from each other. And so when we're calculating these probabilities, what we can use is the fundamental counting principle, which is the probability of A and B happening, which is the probability of A times the probability of B, when we're working with these independent events. So if we look back here, the probability in our first case was 1/2. Right? We could flip heads or tails. Each of these in the second flip still has, you're either going to flip heads or tails. So still a 50-50 chance, a 1/2 chance. And in a third flip, there's still a 1/2 chance. Well, 1/2 times 1/2 times 1/2, 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. There's our 1/8. So there's our fundamental counting principle, the probability of A and B, and in this case A, B, and C, the flipping heads, tails, flipping tails, tails, and tails 3 times. So we can use the fundamental counting principle here. When we're working with an outcome that will impact the other outcomes, then we call these dependent events. So in our example here, we're going to pull a marble out of a bag. And then we're going to pull another marble out. Well, once we pull one marble out, we've reduced the sample space, and that's changing that. Another example could be, what's the probability of drawing an ace from the deck and then drawing a second ace without returning the first card? So if you draw an ace, the probability of drawing an ace now has been reduced because there's less aces in the deck and there's less cards in the deck, so it changes the probability. So let's look at this example here. We got a bag with 3 red, 3 yellow, and 3 green marbles. What's the probability of drawing a red marble followed by another red marble? So the probability of drawing a red 1, and red 2 is equal to the probability of drawing a red marble. So the probability of drawing a red 1 times the probability of drawing the red marble number 2. And what's each of these probabilities? Well, the probability of drawing a red marble initially, well, we can pull one of those 3 marbles, and there's a total of 9 marbles in the bag. But the probability of drawing a second red marble, well, there's no longer 3 red marbles. There's only 2 red marbles. And there are a total of 8 in the bag. And so now we can multiply those out. So we'll simplify these. These are, first, this is 1/3 because each of these are divisible by 3. And this is 1/4 because each of those are divisible by 2. So you actually see the first chance, we had a 1/3 chance of pulling a red marble, but the second marble, there's only and now there's a 1/4 chance, so there's less of a chance of pulling a red marble out. So 1/3 times 1/4, we have a 1 in 12 chance of pulling a red marble and then another red marble. So what this is now is the probability of A and B happening is the probability of A happening, and then the probability of B given A. This is called a conditional probability. So this here, B given A. So the probability here of R2 is the probability of this event happening given that A happened. Since A happened, it affected it, and this is the proper format for writing that formula out. So the probability of the event A happening, and then the probability of event B given A. So that's what we did here. The probability of event A was 3 and 9. The probability of event B, because we pulled a red marble, the probability of event B became 2 and 8. And so that is our independent and dependent events. So again, our fundamental counting principle, if we have independent events that don't affect each other, we're just multiplying the probabilities of them happening. If the events do happen to affect each other, we're still multiplying the events, but the probability of each successive event, if it's dependent on the previous, then we have to modify that like we did up here.